Our next test for convergence of series is the integral test. What's the situation? I'm going to have a function on the real line. It's positive everywhere, it's decreasing, and it's continuous. We're going to have our sequence defined by f evaluated at n, so that means there's a function out there that I can fit my sequence to. What will happen is, if I take the series that goes with a sub n and the improper integral that goes with f of x as our range goes out to infinity, then they're either going to both converge or diverge together. What's our picture look like? Well, we're only going to consider f of x with these three properties. We'll have positive, which means above the x-axis. We'll have decreasing, which means it's coming down. And then we'll have continuous, which means I can just draw it without picking my pencil up off the paper. So we have to have a function that looks like this. In general, we may have functions that we can take the improper integral of, but if they don't satisfy these three conditions, the integral test is not going to apply. So you have to be careful to check this before you actually start doing any work. Okay, let's look at some examples. Okay, we have, this is the famous harmonic series. So we're taking the sum as n goes from 1 to infinity of 1 over n. So if we apply our limit test for divergence to this, note that the limit here for 1 over n is going to go to 0. So this thing passes our divergence test. So we proceed. I can fit my sequence to 1 over x. So the integral test suggests that we check the improper integral from 1 to infinity of dx over x. So we write out our definition of an improper integral. Limit as b goes to infinity of the definite integral from 1 to b of dx over x. Take its antiderivative. That's going to give me natural log of x. Evaluate at b and 1 and take the difference. Natural log of 1 is 0, so we're just looking at natural log of b. And then we let b go out to infinity. And then for natural log, we note that that's going to be plus infinity because the picture for natural log looks like this. And remember, you get that by plotting the 3 points for natural log at e. Natural log of e is 1. At 1, natural log of 1 is 0. And then natural log of e to the minus 1 is just minus 1. So you plot those 3 points, you have a vertical asymptote, connect the dots, and then you'll see that natural log goes off to plus infinity. So conclusion, since this improper integral diverges, our original series also diverges. Next example. Let's try the series for n going from 0 to infinity of e to the minus n. Now, I know this converges because we've already studied this. This is going to be the geometric series with r equal to 1 over e. E is roughly 2.7, so 1 over e is roughly a third. And that's going to mean, since its absolute value is strictly less than 1, we have a convergent geometric series. So let's do this using the integral test just to verify that. I'm going to fit my sequence to e to the minus x. It's a perfectly good function. We're going to take the improper integral from 0 to infinity of e to the minus x dx. So we rewrite that as limit b goes to infinity, definite integral from 0 to b. And then antiderivative of the inside is going to be minus e to the minus x. We evaluate at b and 0. That's going to give me minus e to the minus b minus a minus 1, or 1 minus e to the minus b. Take the limit as b goes to infinity. E to the minus b, or e to the minus x, actually looks like this. So as b goes out to infinity, going that way, we're going to have that e to the minus b is getting driven down to 0. So the limit is going to be 0. So that means the limit of the whole thing is going to go to 1. Since my improper integral converges, the original series converges. So this is convergent. We already knew that because it was a geometric series with the right conditions. Now let's compare the answers. What's happening here? Well, this 1 is telling me the area under the curve. Okay, note that the area under the curve will not be the same as the sum of the series. The area under the curve is equal to 1, but the sum of the series is equal to 1 over 1 minus 1 over e, and that's roughly 1.5 if you guesstimate your 1 over e is a 1/3. So note, although the integral test tells me about convergence and divergence, all it will give me is, well, it'll say nothing about what your actual sum is. So you got to be careful with that. The number that's coming out, not so useful for the sum itself. Let's see why the integral test might be true. So what we're going to do is we're going to draw some pictures and then draw some conclusions from them pictures. First case, let's assume my improper integral going to plus infinity of f of x dx converges. So this is going to tend to a definite number when I take a limit. So the picture I'm going to draw, we're drawing f as decreasing continuous and stays above 0. It's going to look something like that. We're going to have our sequence fitted to the function, so there'll be a sequence of points on the graph which we can mark off, and their heights are just going to be the values of our sequence. So let's note, definition. Now, the function's always positive, so if I take a partial sum of the first n terms of the sequence, that's a sum of a1 through an. Sum of positive numbers means we're getting a positive number, which means we're always bigger than or equal to 0, which means I have a lower bound. Well, let's take a look at the geometry. I'm going to mark off the rectangles that go underneath the curve and marked off by the point for the sequence. The base here is 1. The height is going to be the value of the sequence. That's going to be our a1. So the area of this rectangle is going to be a1. Okay, as I move to the next rectangle, we notice height is a2, base is just 1, and so the area of this one is a2, a3, and so on and so on. So what's happening here? Well, if you think of this just pictorially, what this is saying is, if I take all the rectangles that go with the sequence and sum up their areas, that's going to be less than the area under the curve. Okay, so this is just heuristics. We're saying that this total sum area, which we would call the sum of the series, is less than the value of this improper integral, which is a definite number, so the sum of the series is less than a definite number. Let's be a little bit more rigorous than that, though. So anyway, what's happening here? I have my partial sum, a1 all the way up through an. This is representing areas of rectangles, but we note if I take the curve and chop it off at n, it's a perfectly valid statement to say that the sum of these rectangles is going to have area less than the definite integral going from 0 to n of f of x dx, which is just the area under the curve f of x between 0 and n. Now, this thing here is definitely going to be less than the improper integral as we let n go out to infinity, and we know that's going to be given by a number. So if I track everything out, I have that 0 is less than or equal, then our partial sum s sub n is going to be less than or equal to this number m here. So this inequality I just set up doesn't depend on the n that I used. It's going to be true for all n. So what we've just shown is that the partial sum, a1 all the way up through an, is bounded between 0 and m. We also have that s sub n is increasing. If we look at the partial sum, okay, what are we going to do? To get to the next term in this sequence of partial sums, I'm just going to add a sub n plus 1. Well, a sub n plus 1 is a positive number, which means it's going to be bigger than this number here. That means, all right, that s sub n is increasing. As I keep adding on a sub n's, the thing's going to get bigger and bigger and bigger. Well, what do we have here? We have s sub n is bounded. We have s sub n is increasing. Increasing means we're monotone. So the monotone convergence theorem kicks in, which says that bounded and monotone implies that my sequence is convergent. So the S sub n's are going to converge. We don't know what number to, but we just know it converges. And that means, well, that's our definition of convergence for the series associated to A sub n. So if the improper integral converges, then the series converges. All right. Don't get much of an idea what the actual sum is going to be, though. Now, let's flip it on its head. Let's suppose the improper integral diverges. Now, in this case, since we're just taking a function that's completely above the x-axis, what happens when I take the limit associated to this improper integral? So what are we doing here? I would just take some finite piece of this, compute the area under that finite piece under the curve, and then we're just going to let the limit as this piece I'm chopping off at goes to infinity. That's going to diverge in this case. Well, for this f, the numbers that we're looking at are always positive. And as I keep pushing out, we're just adding more positive area to our number. So the only way that this thing can diverge is to go off to plus infinity. It's not going to do any weird oscillation. It's just going to get bigger, bigger, bigger as I keep adding more stuff on. So what's happening here? Well, I draw the same picture as before, except we're going to put the rectangles above the graph. Heuristically, what's happening? I have all these rectangles above the graph. The graph, when I take its area, is going to go to infinity, so that's going to push the area of the rectangles up to infinity also, because this is always going to be bigger than what's below. So writing that out, we're just saying the partial sum is greater than or equal to the integral from 1 to n plus 1 of f of x dx. But what's going to happen is, as I let the n's get bigger here, they're going to push out to infinity, which means that I let the n's here go out to infinity, they're going to get pushed up by these terms here. So we're going to have s sub n going to infinity also. All right, so that's just pictorial proof of our integral test.